So what we're looking at today is actually another kind of volume problem, but it's not a volume of rotation. Okay? The volumes that we've been doing so far have been these nice symmetrically, like cylindrical shaped things, because we take some kind of a function or a area between functions and we spin it around an axis. So it's all this nice rounded thing. Okay, and if you think about it, what we have then is if we were to cut those objects, the cross section of it would be a circle every time, right? Okay, I mean, you think about even the functions that we were dealing with. You know, here we have this. We revolve that around the x-axis. You know, here's our x-axis going through. Okay, and we have this kind of vase-looking thing, and it goes like this. Ooh, that actually turned out no, maybe not. I spoke too soon. That turned out halfway decent. All right, so you have this thing like this, and all of these cross sections are circular. Okay? Now, what we're going to be doing today is actually looking at three-dimensional objects and how to find the volume of them when the cross section is not a circle. All right? We're not forming this by revolving it around anything. Okay? However, we are going to limit it to situations where there is a known cross-section, and it's a consistent cross-section throughout the entire object. Okay? Now, there are two ways that we could do this. The cool thing is you could draw it the same way, it's just a difference in how you label it and how the function is given. Alright, so first of all here, you'll notice we have this object here that's formed, and you can kind of see it comes to a point. But the cross section in this case is taken perpendicular to the x-axis. Now I know that's kind of hard to read, it didn't print out really well. That's the x-axis and that's the y-axis. Okay? So you've got this cross-sectional piece here that we're dealing with. Okay, here's part of it. And it has a depth of delta x, okay? And here's the other side. All right, you guys can kind of see that, and here's the background, like that. Okay, so there's that cross section. Now, if we're doing this where it's perpendicular to the x-axis, then our volume is going to be the integral from a to b of the area, capital A of x, dx. Now, the capital A of x is the area of the cross-section. So wait, how are we doing area? Now we're dealing with volume. We're going to actually develop this as we look at an example. Okay?
So you don't want to find the volume of the whole thing?
No, we are finding the volume of the whole thing, but we're going to do that by using these little cross-sectional pieces. If you think about it, it's kind of like what we did with the disk method, except they're not disks. They're almost like tiles or something like that, if you want to call it that. Okay? Now, we could also deal with functions that are in terms of y, and we could have this cross-sectional piece be perpendicular to the y-axis. So here's the cross-section right here.
They're so hard to see.
Okay? Yeah, this one printed out worse than the first one. So, and yeah, one of the challenges in this section is the very fact that these are really hard to draw on paper or see in a book and picture exactly what it is. I was trying to think of a good illustration, and I think the best thing I could think of is, any of you guys ever eat star fruit?
No.
No?
Yeah.
Okay. Star fruit?
How did you all change your mind?
All right, so we got a picture of a star fruit here. If you haven't ever seen one before. But the idea of this is you see how the shape of this thing, and I know this is set on an angle here. We're not going to do ones that are on an angle. We're going to do them either perpendicular to X or perpendicular to Y. But obviously we could rotate this. But you see how this shape overall, you know, three-dimensionally, we have this kind of football shape in general. But the cross section you can see is this nice star. And it's consistent, but you'll notice depending on where you cut the fruit, that star would be smaller or larger. Okay? And that's what we're going to have here. Now, we're not going to do star-shaped cross sections, all right? But I thought that was a good real-life example to kind of show us something that at least some of you are familiar with, that would help us understand what exactly we're finding the volumes of. Okay?
Who knew math could be so sweet?
Thanks, Adam.
You're welcome.
All right, so let's actually take a look at an example of one of these, and I will do my best to draw this in a way that'll make sense to you, and develop the formula. I know we already have the formula. Capital A of x dx is what we're taking the integral of. But I want you to understand why, all right? I want you to understand why. All right, so in this example here, we are told that the base of the solid region is the base of the solid is the region bounded by the lines f of x, g of x, and the volume of the solid is what we're trying to find. Now, our cross sections are all equilateral triangles, okay? So let me just illustrate what we're trying to do. It says here the line x equals 0 is one of the lines that defines our base. So that's this right here, x equals 0. This line g of x is -1 plus a half x. So that's this line over here. And you'll notice, by the way, sometimes it's helpful to draw these on an angle, okay? It's hard to kind of see it when we use the normal XY axis, but I'm actually going to take a step back in a second and draw it how you would normally graph it, and then kind of show you the situation, okay? So then the other one, f of x, is the line 1 minus x over 2. That's this right here. So that's the base of this thing, okay? That's the base of this object that we're dealing with, okay? Now, before we go any further, let me illustrate how we would get to this point. Because again, you may not always be given the diagram. So if I were graphing this, first of all, here's my XY axis. And I have, x equals 0. So there's my y axis. I have the line for g of x, -1 plus half x. So here's -1. I got to go up 1 and over 2. All right, so here is this line right there. And then my f of x is a 1 minus half of x. Okay, so here's up at +1. I go down 1 over 2, and that's also going to cross there. Okay? So what I end up with here is I have this as the base of this pyramid shape. Okay?
Holy guacamole.
The difference with this pyramid is that one of the sides actually goes straight up. It's not like one of the Egyptian pyramids. If I were to look at this from the side, one side would go straight up and the whole thing would look like this. Okay? If I looked at it directly from the side, it would just look like a big right triangle. And part of it would be coming towards me, part of it would be going away from me. Okay? Again, the challenge of 3D drawing on paper or on a screen. Okay? So we have this, and then I want to show you here what we're talking about with these cross sections. So I'm going to switch over here to purple. Okay? And what we have is if I were to try to take a cross section of this, you know, and I'm looking at it straight from above, all right, I would have this triangle, this equilateral triangle that's coming up here, but since I'm looking at it from directly above, I can't really see the point that it's coming to. Okay? But that triangle we could call, or that triangle, kind of tile, if you will, is going to have a depth or a height, you could say, of dx. All right? Now, let's take a look at this on this drawing, okay? This one, it's a whole lot easier to see. Basically, all we could see on the other one was this right here, okay? Here is our cross section. But what we're doing, just like we dealt with the rectangles beforehand when we were doing integration, and when we were doing volume, we worked with discs. Here, we're going to look at these little, in this case, triangular prisms. Okay? So there's kind of a tile or a prism, if you will. And what we're going to do is we're going to find the volume of this prism. Okay? So, if I were trying to find the volume of just that piece, I would get the area of the triangle, and this is an equilateral triangle, so I'll label it like this. The area of the equilateral triangle times the height. Well, the height, we already said here, that's a distance on the x-axis, right? That's a distance on the x-axis, so we're going to call that dx. Okay? So times whatever that dx is. Now, think with me here. If I want the volume of just that piece, okay, that's what I'm going to do. However, I don't want just that piece. I want this entire thing. So I want this little triangle down here. See that? I want that little triangular piece. I also want the one that's up here. Let's try that again. Okay. So here we have our triangular prism. And again, all of these we could say have a volume where we've got a dx and we multiply it by the area of that equilateral triangle. Okay? So I hope you guys can start to kind of see where we're going with this. Are you kind of seeing it? Okay? It's actually the same concept we used with the disk method. Okay? And with our other stuff, our other integration as well. Okay? In the disk method, what we did is we found the volume of those little cylinders. Well, the volume of a cylinder is the area of the base times the height. The height was the dx, and the area of the base was pi r squared. The only difference between that and what we're doing here is that our base is not a circle anymore. Our base in this case is a equilateral triangle. So we're going to get to that part here in just a sec, but I want to actually make this whole connection here first. So this volume equals the area of the equilateral triangle times dx is just one of these little slivers. Okay? What I have to do in this case is I actually need to add up all of those little slivers, right? So I'm going to take the sum But again, that's only going to give me an approximation. How am I going to get the best approximation?
If you
The limit
As infinity. That's divisions approach infinity.
as the number of divisions approach infinity, right?
isn't that the definition of an integral?
That is the definition of an integral. When you're taking the limit of the sum, when we make the number of little slivers go to infinity, so that dx is approaching 0, okay? That's what we're doing here. We're going to take the integral from a to b, wherever we're starting to wherever we're finishing, of the area of the cross section and that area of a cross section is going to be written as a function in terms of x. So we'll apply it here with our equilateral triangle in just a moment. Dx. Okay? That's what that formula, that's how we get that formula, guys. Okay? Now, let's look at it specifically with this function here. Okay? So I want to look at, I first of all want to come back up here and look at what the height of this is going to be. What would the height of this, or the how long that rectangle is, be?
F of x.
It's not just f of x.
The sum of gx and f of x, like their y-axis.
Okay,
Their absolute value.
G of x minus f of x minus g of x?
there we go. You're on the right track there. Yeah, we're going to take the upper function minus the lower function, right? So that right there is f of x minus g of x. Okay? F of x minus g of x.
But also we need to know what's the point there where they cross. So we set them equal to each other to find that point, and it's gonna be the height.
We will. Well, that actually, that's what's going to help us. It cut it off at 0, and those intersect at 2. That's actually going to be telling us that we're taking the integral from 0 to 2. Okay?
You're just gonna find.
So we're going to get to that here. Okay?
So why should you find the area of the small piece instead of the volume of the small piece?
Well, the volume is the area times its depth. Well, the depth is the dx, right?
Yeah, that's why I have the dx.
So yeah, so here, what I need here is I need to figure out what that area in terms of x is. Okay? So watch this. This is where you gotta know, you gotta use your geometry skills a little bit here. Okay? So now I'm gonna draw another diagram. Okay? Another diagram. This one's relatively simple. It's just an equilateral triangle. However, I just showed that the side of this equilateral triangle is f of x minus g of x.
Good.
Right? Now, for ease, I'm going to use my side s until I get to the end. Okay? Or else this will get really messy. Alright? So what we need to do is we need to figure out how to find the area of an equilateral triangle.
Oh, you can do a side square root of 4 over 2,
1/2 base 2.
right?
You're on the, you actually almost got it. It's actually side times the square root of 3 over 2
Yeah.
or over 4.
Something
Got to
like
remember. Anyways, we'll just develop it, right? If it's equilateral, what are the angles?
that.
60.
60. So, if I cut this like this, then this side right here is s over 2. And what would this be right here? The height.
Or you can do the sine.
Square root
S square minus S over 2 square.
Okay, yeah, we could use the Pythagorean theorem because that's s. This is a 30, 60, 90 though too. We could get it even faster. You remember your x radical 3 and 2x for the pattern?
Two S.
So it's S over 2 radical 3.
That's right, s over 2 times radical 3. That's the height,
Oh, yeah.
okay? Now, however you figure that out, that's fine. Pythagorean theorem, right triangle trig, knowing the pattern for a 30, 60, 90, I don't care. You'll get to this point eventually, okay? Now, so the area of a triangle, you guys obviously know, is base times height divided by 2. Well, the base is s, the height is this s root 3 over 2, and that's all over 2. Okay? So, we have s squared times radical 3, and that's all over 4. So that's the formula for an equilateral triangle. If you remember it, awesome. If you don't, you know how to find it now. Okay?
Are we working only with equilateral triangles in this section?
No. But the principle is the same. Whatever the shape is, you got to write its area as a function of x. Okay? Mm-hmm.
So, if we're doing the integral, would it be root 3 over 4 times the integral from 0 to 2 of s squared, which would be like half of x
Oh,
minus
not 2.
one.
Yeah, look at this. Using what we just did, I'm taking the integral from 0 to 2 of s squared, and I've got the times root 3 over 4 on the outside, so I don't have to mess with it till the end. That's exactly what we're going to do. And since we know that s is f of x minus g of x, check out what we've got. We've got root 3 over 4 times the integral from 0 to 2 of f of x minus g of x, and that is squared. Remember before when I told you what we were doing before, you had to make sure you squared first, then subtracted?
Yes.
Here we're subtracting first, then squaring. Okay? So our volume is this. I have a root 3 over 4 times the integral. Now I'll go ahead and plug in f of x and g of x. F of x is 1 minus x over 2. G of x is a negative 1 plus x over 2. Do a little more simplifying.
Shouldn't you put a big bracket to show that your dx is modifying both?
There? Yeah, you can.
But is that obligatory?
It's not, because like the integral symbol and the dx are kind of like a grouping. It's kind of like a bracket. Everything between those is what you're taking the integral of. It's kind of an understood thing, but yeah, you could put it. So let's see, 1 minus a negative 1 is 2. Negative x over 2 minus an x over 2 is a 2x over 2, or just minus x. Okay? And now we're down to take the integral. Piece of cake.
We have to square it.
Yeah, square it. Yeah, square it. So, FOIL, take the integral, evaluate it, and you've got your results. Okay?
Wow.
So, root 3 over 4 times the integral from 0 to 2 of 4 minus 4x plus x squared dx. So we have 4x minus 2x squared plus x cubed over 3. Evaluated from 0 to 2. And then multiplied by the root 3 over 4. Okay? If I plug in 0, it's 0, so I know it's just whatever I get when I plug in 2. Okay? So 8 minus 8 plus 8/3
So 0.3 multiplied by
minus the 0. So this whole thing, 8 minus 8 is 0. So I get a 2 root 3 over 3. And that's going to be my volume.
So all you're doing is the same thing as the washer method.
Is it the same as 2
Yeah.
over root 3?
Yeah, we're doing the washer method or the disc method essentially. It's just we don't have a round base or a round cross section. All of the things we did before had round cross sections. Here we have a different cross section.
Just like the same thing almost for the area. For the area, you find a small area and multiply it to find the big. For this one, you find the small volume and get the integral, find the big.
That's right. That's right. Okay?
I have one question.
Mm-hmm.
So, why does like the shape of the like the image is like triangle instead of like saying like just upper, like just like go straight to unlimited? Do you get what I mean?
Because we made it be that way.
Oh.
We said, here's the thing, we could use these same two lines and we could make a totally different shape if we said all the cross sections are semicircles
Okay.
or all the cross sections are squares. It would look totally different, but we could actually use the same f of x and g of x, just make a different shape using those. Okay? So yeah, you're gonna be told what the cross section is, because if they didn't, then you could make the cross section whatever you wanted and you'll have totally different looking things.
Okay.
So, yeah, that's a great question. Yep.
So in this one, the cross section is perpendicular to x. If it's perpendicular to y, do you just do the same thing except in terms of y, integrate with y?
You'd have to rewrite these in terms of y, you'd have to figure out what the bounds would be in terms of y. Yeah, you'd have to modify it that way. But, okay?